Okay, maybe again, and I'm here to explain to you about how to solve another problem example about internal force and internal moment. Okay, the problem that we are going to talk about is this particle problem. Okay, as you can see here, the problem is like this. Okay, and the thing that you have to know is, okay, this is the problem. And the thing that you have to know, the one that is in question, is the stress distribution along ABC section. Okay, this particular section, which is part of the member ABCE. Okay, this one. Okay, and that's the question. In order to solve that, what you're supposed to do as usual at the beginning is to solve for the external forces at C, at A, and because the shape of BE is like this, okay, we can solve for external force at B as well, which represent this particular force, 80 kilonewton. Okay, and then after that we do the cutting. Okay, before that, I think I will start explaining about how to solve the external forces first. Okay, if we draw the free body diagram of A, B, C, E, this is the particular free body diagram. As you can see there are three external forces, Cx and Cy, and FAD. Okay, and 80 kilonewton here is actually coming from this particular distributive force, 20 kilonewton per meter, multiplied by 4 meters. Okay, and then I put it exactly in the middle, where the distance is 2 meters from the right and 6 meters from the left. Okay, and because of that, now I can, because all things are complete already, now I can calculate for the external forces, FAD, CY, CX. Okay, using sigma moment at C, yeah, I will be able to calculate for FAD. So if clockwise is, if counterclockwise is positive, so 80 kilonewton per meter multiplied by this, the moment arm 8 meters. Okay, this one minus FAD sin theta. Okay, remember that theta there, we can find theta using these two values. So theta is supposed to be arc tangent of 2 divided by 4, arc tangent of 0.5, which is 26.565 degrees. Okay, then using FAD sin theta, the direction is supposed to be clockwise, that's why it's positive. Yes, that's why it's negative, because counterclockwise is positive. So FAD sin theta multiplied by 8. Okay, this one. 8 is this distance. Then plus this one, 80 kilonewton multiplied by 2 meters, the moment arm. Okay, and after rearranging the terms, we will be able to get that FAD is equal to 800 divided by 8 multiplied by sin theta. That's why our value of FAD is 223.6 kilonewton. Okay, then we follow up with sigma fx equal to 0. And for sigma fx equal to 0, the horizontal forces that we have is only Cx and the x components of FAD. That's why there we have FAD cos theta, going to the left is positive, minus Cx equal to 0. Because FAD value, we already got it, this one. That's why we will be able to get the Cx value. Cx value will be FAD multiplied by cos theta, which is 200 kilonewton. Okay, then after that, we use sigma fy equal to 0. For sigma fy, we have several components there. Cy, 80 kilonewton here, 80 kilonewton here, and F8, the vertical component of FAD. Okay, if going up is positive, so FAD sin theta plus Cy positive. Okay, both of 80 kilonewton are going down, so minus 80 kilonewton. Okay, that's why our value of Cy will be 60 minus FAD sin theta. Okay, FAD sin theta in this case is 100. Okay, 223.6 kilonewton sin 26.565 degrees. The value will be 100 kilonewton. So 160 minus 100 will be 60 kilonewton. So now we already solved for Cx, Cy, and FAD. That's why then the next one is because I want to isolate only the section ABC. That's why I want to remove the 80 kilonewton, yeah, to this particular cutting. So what I want to do, what I will do is I will cut this particular section, BE section, at this particular location. Okay, and this is the free body diagram. So 80 kilonewton, By, Bx, and Mb is the one that I will transfer to the section ABC. Okay, using sigma Fy equal to 0, what I will get is By minus 80, because only 80 kilonewton and By there, which is the vertical force component. By minus 80 is equal to 0. That's why my By is 80 kilonewton. Then using sigma Fx equal to 0, there is no horizontal components beside Px. That's why this is the only one. Px is equal to 0. Okay, then sigma moment at P equal to 0. Okay, if counterclockwise is positive, so Mb, okay, plus, because 80 there is counterclockwise as well, 80 multiplied by the moment arm 4 meters, okay, equal to 0. That's why our MB will be the same as 8 minus 80 multiplied by 4 is minus 320 kilonewton. The minus there means the direction here is incorrect. Instead of counterclockwise, the direction is supposed to be clockwise. That's why in the final free body diagram, this one, instead of drawing the this one, the direction is supposed to be clockwise, 320 kilonewton. That's why after I translate, the direction is supposed to be counterclockwise. This one, 320 kilonewton positive, counterclockwise. Okay. Then I draw all the other forces as well. Just now I found out that Cy is 60 kilonewton, Cx is 200 kilonewton. So this one is 200 Cx. This is Cy 60 kilonewtons, and this is FAD. Okay, which is 223.6 kilonewton. Okay. Beside that, I draw as well that all the results from this particular cutting. Okay, but in the opposite direction. So Py, instead of going up 80 kilonewton, it's going down 80 kilonewton. This one going down. Px is 0, still 0, and the Mb, because the actual direction here, the actual direction there, okay, I will continue again. I'm sorry, just now my stylus battery is running out. Okay. Yep. So after we transfer all the forces there, okay, after we transfer all the forces, the 80 kilonewton Py and the moment to 20 kilonewton, okay, So now we got the complete free body diagrams for the cutting process. Okay, for this kind of problem, you can see that we can represent the internal force and internal moment distribution using only two cuts. Okay, the first cut, which represents the x between 0 to 4 meters. Okay, because the discontinuity is happening at here and here, so one equation will be enough from here to here. Okay, and the second cut is representing the x from 4 meter to 8 meters, because the discontinuity started from here and ends here. Okay, there is a discontinuity here and discontinuity here, so one equation is supposed to be enough to represent from x equal to 4 to x equal to 8. So there are total two equations and two cuts. Okay, the next thing that I will do is to solve the first cut. Okay, this one, the first cut there, I cut it here. Okay, I cut it here, and the free body diagram for the cut will be like this. You can see there. Okay, the external forces there is supposed to be only 223.6 kilonewton, and then the distance from the left to the cut, okay, will be x. This one is only x, and then I draw as well the positive shear force, normal, and moment like that. Okay, using sigma fx equal to 0. Okay, I will be able to find the axial force value if going to the left is positive. Going to the right is positive. So n minus 223.6 cos theta equal to 0, and my normal force value is axial force value is 200 kilonewton. And then using sigma Fi equal to 0, the only forces that has a vertical component is 223, the vertical component of that, and V. So if going down is positive, then what I will get is V minus 223.6 kilonewton multiplied by sin theta is equal to 0. That's why I get value of V equal to 100 kilonewton. Okay, then sigma moment to the right of the sigma moment at this side, okay, the right side, equal to 0. What I will get there is counterclockwise positive, okay, moment minus 223, because this one it will give us clockwise moment 223 kilonewton sin theta, okay, the vertical component of it, multiplied by the moment arm x in this case equal to 0. This one. So m minus 223.6 sin theta multiplied by x. And then what I will get is this. M is equal to 100x. Okay. Then I will move to the second cut. Okay. For the second cut, I haven't solved it yet. But I believe it will be easier for us to solve it from the right. Okay. And before that, I believe it is better for us. Okay, I will continue again. So this is the free body diagram of the second cut. As you can see here, this is the free body diagram of the second cut. Okay, this is the free body diagram of the second cut. So I will continue for the second cut. Okay, for the second cut, as usual, I will start with the sigma fx first, equal to 0. In this case, the only horizontal component will be just n and 200 kilonewton. So if going to the left is positive, what I will get will be like this. So my n value will be 200 kilonewton. Then, using sigma fy equal to 0, there are 3 vertical components there. V, 60 kilonewton going up, both going up, and 20 kilonewton per meter going down. Okay, and I need to give information about the distance here, because x is the distance from the left edge to the cutting. That's why here the distance here is supposed to be 8 minus x. Why it's like that? Because remember, the x is from the left edge, the dimension from the distance from the left edge. So if the second cut is here, so the distance there from the left edge to the cut, it will be x. And the distance from the left edge to the right edge, total will be 8 meters. So that's why this one, because from this to this is 8 meters. So the distance from the right edge to the cutting, it will be 8 minus x. That's the thing. That's why the distance there is 8 minus x. Okay, the distance there, 8 minus x. Then using sigma fy equal to 0, if going up is positive, what I will have is v plus 60 minus 20. 20 kilonewton per meter is the distributed force. I have to multiply it with the distance there. 8 minus x equal to 0. Okay, not the distance, but the length of the distributed force. Okay, so what I will get there will be v is equal to, this one is minus 180 plus 60, so minus 100 plus 100 minus 20x plus 100. That's our v. Okay. Okay. In order to draw it later, it will be much easier if I know the value of v at x equal to 4. In this case, the value of v at x equal to 4 is 100 minus 4 times 20, which is 80. So 20 kilonewton. And v at x equal to 8 meters. In this case, will be 100 minus 60. So in this case will be minus 60 kilonewton. Okay, then using sigma moment on the left side to make it easier. What I will get there will be, if clockwise is positive, moment minus 60 multiplied by the moment arm, 8 minus x, because it's counterclockwise, so it's negative, and plus 20 from the distributed force, it's clockwise, multiplied by the length of the distributed force. In this case is 8 minus x, and the moment arm. The moment arm will be 8 minus x divided by 2. Only this 3 component moment. Yep, only this 3 component. And this one will be equal to 0. Okay, I will try to solve this first because it's slightly longer. Minus 480 plus 60x plus 10 multiplied by x squared minus 16x plus 64 equal to 0. In this case, my moment value will be minus 10x squared plus 60x minus 60 plus 100x in this case, then minus 640 plus 480. minus 480 is minus 160, I believe. Okay, 640 minus plus 580. Yep, it's correct. Then, as usual, I will have to check the moment at x equal to 4. What is the value there? The value there will be minus 160 minus 160 minus 160 minus 160 plus 400. So the moment there is supposed to be 80. Okay, supposed to be correct. And then the moment value at x equal to 8. Okay, minus 640 minus 160 plus 800. Okay, the value there is supposed to be 0. Okay, this one is correct as well. Then, in order to know the correct diagram, I need to know the maximum moment as well. So in order to find that, I will find it using this, the first derivative of the moment. Equal to 0, because the gradient at the gradient equal to 0, that's the maximum positive, the maximum or the minimum point. Okay, so the things happen at x equal to 5 meters. So the moment max happen at x equal to 5 meter. The value is okay, 25 minus 250 plus 500 minus 160, 90. The value is 90 kilonewton meter. Okay, now we can draw. We can draw all the things here. This is just now the n. This is just now the phi. This is just now the moment equation. Okay. From x equal to 0 to 4, the axial force is 200. Okay. And the axial force will stay the same at 200 for x equal to 4 to 8. 200 kilonewton there. Then for shear force from 0 to 4 meter, the value of the shear force is 100 kilonewton. Then after that, it drops to 20. Okay, 100 kilonewton here. Then it drops to 20. Okay. Then after that, it's going linear and going down linearly until it reaches 60 kilonewton when it reaches x equal to, this one is 20, right? Yes, just not 20, 60 around here when x equal to 8. So yep, linear like this. This is 100 here, 100, and here at this point is 20, then at this point is minus 60. Then now we draw the moment diagram. The moment diagram at x equal to 0 is 0, and at x using this equation, and x equal to 4 is supposed to be 400, roughly around here. So this one is 400. It's linear, going like this. Then after that, it drops. When x equal to 4 meters, it drops to 80, roughly here, 80. Okay, then it follows this particular equation, quadratic equation, minus 10x squared plus 100x minus 160. Okay, and it peaks at x equal to 5. This one is around 6. This one is around 5. Okay, it peaks here at x equal to 5, and then it's going down. Roughly like this. Yeah, the graph is not smooth, but it's roughly like that. Okay, the value here is 80, and the value at the peak is 90 kilonewton meter. So this is the final answer. Okay, I hope it helps you to understand the how to solve this particular problem. Okay, thank you very much for listening.